Welcome to the third lecture of Continuous Mass Distribution CCD03. In the first two lectures, we have seen what is the meaning of the mass density, and we focused on one type of mass density, the linear mass density. The linear mass density is employed or used when the mass is distributed over any length, like rod, thread. The length can be rectilinear, straight, or curvilinear, that is, curve. Now, this lecture will deal with the surface mass density, the second kind of mass density. And in the description below, a link is given for the test based on this lecture. So after the lecture, you can test yourself how much concepts you have grasped. And before proceeding with this lecture, if you haven't gone through CCD01 and CCD02, in which we have done the linear mass density, I recommend you to first go through these two lectures, then come back to this CCD03. And after CCD03, you can attempt the test with the help of the link given below to assess yourself how much you have gained the command over innovative and conceptual problems. Now, see, in this series of surface mass density, let's see what will be the roadmap. So, first of all, we will explore what will be the meaning of the surface mass density, what is the significance of the surface mass density. Then we will see the calculus skills. One skill will be we will take infinitesimal element, the calculus element. So the first skill will be taking a circular element in a plane. We will see if there is a plane, like this is a plane is a flat surface. So we'll see how we take the element, say, of radius r and thickness dr. So this is one of the major skill of calculus which will be applicable throughout the subject. So all these skills we will learn in this series of lecture, the surface mass density. Then we'll see how we'll take a circular strip on a spherical surface. Okay, then the second skill you will learn how we will take a circular strip, something like this, on a spherical surface. What will be the area of this strip? How many such strips will be there? What will be the angular position and linear position of such strips? And the third skill will be if there is a conical surface, so how we will take a circular strip on the conical surface. So these are the major skills of calculus which we will explore in this series of lectures, surface mass density. Okay. So first of all, let's see what is the meaning of surface mass density and when we use the concept of surface mass density. So in the previous two lectures, you have seen when the mass is configured or distributed over any length, then we use the concept of linear mass density lambda. The surface mass density is denoted by the Greek symbol sigma, like this. Okay, this is the symbol of surface mass density. And we use the concept of surface mass density when the mass is distributed over a surface. When a mass is distributed over a surface, okay? We use the concept of surface mass density when the mass is distributed over the surface. Now, the surface can be plane or the surface can be curved. Okay, now see, suppose you have a plate. You have a plate and there is some mass of the plate. So you can see plate is a surface. Plate is a surface. So in this case, the mass is distributed over the surface. So in this case, we use the concept of surface mass density. Okay, suppose we have a disk. We have a disk. Okay, and our disk is a surface. So here also the mass is distributed over a surface. So here also we use the concept of surface mass density. Now suppose we have a hollow, thin sphere. Okay, you can also call it as a spherical shell. Okay, so it's a very thin envelope. So if you see the mass is distributed over a spherical surface, in this also it's a spherical surface. Inside it is completely hollow. So mass is distributed over a spherical surface. So here also you use the concept of surface mass density. So these are some of the illustrations where you can see how the mass is distributed over the surface, where we use the concept of surface mass density. So let's see how we define the surface mass density. Already we have seen in lecture 1 that any kind of mass density, whether it is linear mass density, whether it is surface mass density, whether it's volume mass density, it is a microscopic property. That is the property of a point of the object. It may vary from one point to another point in the same object. Any density, surface, linear, or volume may vary from one point to another point on the same object. That makes it a microscopic quantity. So suppose you have some surface. This is some surface, okay? And we have a goal. We need to find the surface mass density at this point, P. Okay, we have to find what will be the value of sigma. Sigma means the surface mass density at a point P. So what you will do, you will take an infinitesimal mass element at P. I'm making a highly magnified figure. Suppose this is the infinitesimal mass element. This is calculus element. Infinitesimal mass element, say of area dA. Like in the linear mass density, we were taking the length dl. In this case, you will take the area dA. And I'm making a highly magnified figure. Actually, it is very infinitesimal. And such elements will be continuous in nature. Already you have seen lecture 1 how an extended object is treated as an assembly of infinitesimal elements in continuous manner. So suppose I'm making a highly magnified figure. This element has an area of dA and it has a mass of dm, infinitesimal mass, dm. So at this point, at the location of this element, the value of sigma will be dm divided by dA. So this is the formula for sigma at any point. This is the formula for sigma at any point on the object. If you are taking an element, if you're taking an element at any location of the object, the element has a mass dm and the area dA. So the surface mass density at that location will be dm by dA, mass divided by the area, and it will give you the SI unit of sigma. It will give you the SI unit of sigma as what? So mass has a unit of kg and area is denoted in unit by meter square. So the SI unit of sigma is kg per meter square. Okay. Now conversely, if you write, if I say if I have an element which has an area dA and the surface mass density sigma, so its mass dm can be written like sigma times dA. Simply see, the equation is same. Simply you're changing the subject of the formula. You're changing the subject of the formula. You are making dm as the subject. So if sigma is given for the element, you can make dm as the subject and dm will come to be sigma dA. Now, of course, we have seen in lecture 1, if there is any extended object with a size, so an extended object is considered as an assembly of a large number of infinitesimal elements, and all such elements are continuous in nature. One cannot be isolated from another element, right? They are continuous in nature. So it is a mass of one such element. Now, if you want to find the total mass of the object, so mass of all the elements need to be added, correct? As you did in the linear mass density. And in the language of calculus, addition denotes integration. So we can write the total mass, say m, is integral of dm. So it implies that the total mass will come to be integral of sigma times dA. So that is a formula for finding the total mass, and this is the universal equation. It has no limitation. You can apply it whether sigma is variable or whether sigma is constant. And same approaches will be applicable, as I told you, in electrostatics and electricity. Here you are dealing with the mass density. There it will be the charge density, but the formula and approaches will be same. Only in place of m, we will have q, the quantity of charge. Now here the question arises whether sigma will come out or not. So it depends on the nature of the object. It depends on the nature of the object. Now if you take a special case, if you take a very special case as we have done in linear mass density, if the mass is uniformly distributed, okay, if the mass is uniformly distributed, such an object is called homogeneous. Such an object is called homogeneous. So in this case, all over the object, sigma at each point will be same. So you can say sigma is constant over the object. So in this case, the value of sigma will come out of the integral, and what is left is integral of dA. And integral of dA will give you the total area. So in this case, you can write this special formula, m is equal to sigma A. Okay, m is equal to sigma A, or if you make sigma as the subject, so you can write or sigma is equal to total mass divided by total surface area. Now this is a very special limited formula when your object is homogeneous. You cannot apply this formula in all the cases. When it is given the object is homogeneous, okay, when it is given that object is homogeneous or the mass is uniformly distributed, then we will apply this equation. And of course, when nothing is given about the variation of the density over the object, then we assume that the object is homogeneous. All the formula for the center of mass, the electric potential, and your moment of inertia, gravitational field, electric field. So when you derive this formula, and if no other information is given about the variation of density over the object, then we will take a model in which we assume a constant density like this, and this formula will be applicable in most of the problems and situations. We will also see when sigma is variable. When sigma is variable, it is changing on the same object. So sigma will not come out of the integral, and we will see in the lecture how we solve both kind of problems. Okay, so this is the generalized approach. This can be applied in any case. Even if sigma is constant, then also you can apply the calculus approach. It is a calculus approach is the most generalized approach, but this approach you can apply only when you are sure that sigma is constant. Then only you can write sigma is mass by area. Then only you can write sigma is equal to what? Mass divided by area. If sigma is variable, number one, or if at the very first place we don't know whether sigma is variable or whether sigma is constant, then go for this approach. Don't bring sigma out of the integral, okay, because this is a generalized approach. So for a constant sigma, that is when the mass is uniformly distributed, or you can say the object is homogeneous. So you can bring sigma out, and your formula will be m is equal to sigma A, or sigma is equal to m divided by A. So this is the meaning of surface mass density and the basic formula for the surface mass density. Now see, if you talk about a uniform or homogeneous objects, so I will give you some illustration. So if I see illustration number one, okay. So suppose you have a square plate. Okay, we have a square plate of side A, and it has a mass m, and it is given it is homogeneous. Okay, it is given that it is homogeneous. So if I say what will be the surface mass density of this square plate, so you will say since it is homogeneous, this is the key point, it is homogeneous, we can apply the total mass. First of all, we will use sigma because the mass is distributed over the surface. This will trigger you, this will hint you which kind of mass density we have to use. So in this case, the mass is distributed over the surface. So we are going to use sigma. So sigma will be total mass divided by the total surface area, and the area of a square is A square. So this is the value of sigma. This is the sigma for this square plate. Now suppose in this very problem, we say that we cut out, we are cutting out a disc of radius r from this plate. Okay, from this plate. So what will be the mass of disk? We have to find the mass of the disk. Okay, so see what will be the concept in such problem. Disk is the part of the square plate. So its material is same as that of the square plate. And the plate is homogeneous. So the density of the disk will be same as the density of the plate. First key point. Disk is part of plate. So sigma for disk is same as sigma for plate. Say sigma. It's uniform. No? The object is homogeneous, so sigma won't change. And already you got the value of sigma. Now let m dash be the mass of disk and its area is A dash. Okay, this is the assumption we are taking. Now we know since disk is the part of the square plate and the square plate is homogeneous, so of course your disk will also be homogeneous. So we can apply the formula mass and mass you're taking m dash is sigma. Don't put dash over sigma because sigma is same as that of the plate. So we are not putting prime or dash over sigma into area of the object, that is A dash, and the radius of this is r. So m dash will come to be sigma into pi r square, that is the area of the disk. So m dash come to be, now put the value of sigma, that is m divided by a square into pi r square. This is your answer. Okay, so this is first illustration how we work with homogeneous object. Okay, this is the first illustration how we work with homogeneous objects. First of all, you will find the value of sigma. You will find the value of sigma by dividing the total mass by the area of the surface. Then if you're cutting out or considering, even if you're not cutting out or considering any region of surface on the same object, and you have to find the mass of that region, so that mass will be sigma times the area of that region, and sigma value you can put from there. Now, in most of the MCQs where we can apply one fingertip point, FTP. Fingertip point, FTP, for MCQs and for instant answers. See, whenever some surface has a mass and it is homogeneous, okay, and say you're taking two regions on the surface, there is one region of area, surface area, say A1, and it has a mass M1, and there is another region of surface area, this patch, it has a mass M2 and area A2, okay. So we know the whole object is homogeneous. It is given it is homogeneous. This is the condition for this FTP. This is the condition for this FTP. It means sigma will remain constant over the whole object. And we know m is equal to sigma times of A. So m1 will come to be sigma A. We won't write sigma A1 because sigma is same over the complete object. So sigma don't have a subscript 1 or 2. It will be same for both the patches. M2 will be sigma times of A2. So therefore, M1 by M2 is same as A1 by A2. So this is one of the FTP. Whenever we have some homogeneous object, so the masses of two portions of that homogeneous object are in the same ratio as the area of the two portions. The masses of the two portions of that homogeneous object are in the same ratio as the area of the two portions. Okay, this is important. You can apply for homogeneous. The limitation is when you can use this formula when the object is homogeneous. Okay, so suppose we have a plate something like this, and this side is A and this is your 2A. Okay, and this is also say A, and we are dividing it in two regions. Say this is having a mass M1 and this is having a mass M2, and it's a homogeneous plate, everywhere sigma is same. So you can write M1 by M2 is area 1 by area 2, And what will be area 1? So this will have area 1, this plate portion, and this plate portion has an area 2. So this will be length into breadth a square, and this will be length into breadth 2a into a square, 2a square. So this will get cancelled away and you'll get 1 by 2. So m1 comes to be half of m2. This is the relation between m1 and m2. And if you're given the total mass, say total mass is equal to m, so another equation will be formed, m1 plus m2 is equal to m. Now from these two equations you can simultaneously solve to get m1 and m2 in terms of m, correct? So this is how the things work for homogeneous object, and this is the fingertip point. For homogeneous object, the ratio of the masses will be same as the ratio of the surface areas. Now say here we have an illustration. Suppose we are given a disk and its radius is given to be r, and it's homogeneous in nature and it has a mass m. Now the first part is, what will be the surface mass density of this object? So since it is homogeneous, you can write total mass by total surface area. So we'll get m by pi radius square, that is pi r square, correct? This is the first answer. Now second part says, find the mass of a piece of disk in the form of an equilateral triangle of side A. Now what we have to find? We have to find what will be the mass from the portion of this disk, and the portion is in the form of equilateral triangle of side A. So if you just focus on this equilateral triangle, correct? So it has a side A, and this is A and this is 60 degree. So the height will be, we know basic geometry, a cos 60, a sine of 60 degree, that is a root 3 by 2. And we can write the area of the triangle as half multiplied by base. So base is a into height, a root 3 by 2. So the area will come to be a square root 3 by 4. This is the surface area of a plate, surface area of any plate or surface in form of an equilateral triangle. Now let the mass of this equilateral triangle be m dash, and let the area of this equilateral triangle be a dash. Sigma will remain same because already we have seen right now it is simply the portion of the original object. Original object is the disk of mass m and radius r. So its material is same. To the equilateral triangle will have same sigma as that of the original disk. Okay, so we can write m dash, since it is again homogeneous, same portion, same material. Sigma won't have any dash or prime. It has the same value as earlier, multiplied by a dash. So m dash will come to be sigma a root 3 divided by 4. Now you can put the value of sigma, that came to be m divided by pi r square a square root 3 divided by 4. So this is the answer to part B. Okay. Got it? Now see illustration 2. Consider a uniform disk of radius r with a scooped out portion in the form of circle of radius r by 4. Find the surface mass density of this object. The mass of the disk needed to fill the hole as to get a complete uniform disk. Now in such problem, one thing is very critical. In such problem, you will see such problem in center of mass, in gravitation, in moment of inertia, in electrostatics, so on and so forth. One thing is very critical. The original mass is related to which object? First thing you have to focus on for finding the original sigma, for which object the mass is given. Like here you see we have a disk, and from the disk a cavity, a hollow space has been made. Something has been scooped out. That is a cavity, creating a hollow space. And the cavity is in the form of a circle. So it is possible that you can be given What are the possibilities? It depend on the nature of problem. You can be given that when the cavity has not been made, then the mass was m and radiuses are. So this is before making the cavity. So in this case, if it is homogeneous, sigma will come to be m divided by a, that is m divided by pi r square. Or it can also be said that m is the mass of this object after making the cavity. It can also be said in the situation of the problem that it has a radius of r by 4, okay, and this has a radius of r. So this object has a mass m. See the difference. In this case, you are given m is the mass of the complete disk before making the cavity, because of course cavity cannot be in the complete disk. This is what it is being said, m is the mass of this object when from the disk a circular portion has been scooped out, correct? So if this information is given, so sigma will again be mass by area. So in this case, area will be what? Area you will take about the for the surface over which the mass is present. So total area would have been pi r square, but there is a cavity, so we have to subtract this area. So it will be pi r by 4 square. So in this case, your sigma will come to be m. You can take pi r square as a common factor. 1 minus 1, 4 square will be 16. So you'll get 16 times of m divided by pi r square. 16 minus 1 will be 15. So this will be the value of sigma. Okay. So how you decide sigma at the very first place, it depends what information is given. Which object is associated with the given mass. I guess it is clear to all of you. Simply don't think every time that sigma will be m by pi r square. Had something been given like this in the problem, then you have to apply this approach. So in such cases, for finding the sigma, you have to see for which object a mass is given. So see, that's why I have not given the mass earlier, because I have to explain these two things, then I will write the mass. So suppose here it is given, let m be the mass of indicated object. See the problem. It is not given that m was the mass of the complete disk. It is given m is the mass of indicated object. Indicated object is this object, the object with the cavity. Okay. So what will be the value of surface mass density? Now it is straightforward. We have done here. So since m is the mass of indicated object, so and we are considering a uniform homogeneous disk. So we can apply the formula sigma is total mass by the area over which the mass is present. You have to take the area over which the mass is present. There is no mass in the whole. So mass of this object is m. The area will be the complete area of the disk pi r square minus the area of cavity, that is pi r by 4 square. Already you did this thing here, correct? So your answer will become to be 16 times of m divided by pi r square multiplied by 15. That is your answer to first part. Now second part is saying find the mass of the disk needed to fill the hole. Now we have to bring some disk. You have to bring a disk and put it here in the cavity so that you can get a complete disk as a homogeneous object. So find the mass of the disk needed to fill the hole as to get a complete uniform disk. So one thing is for sure, to fill, if you are filling that hole, you have to bring a disk of radius, how much? R by 4. And since you want, your goal is to get a uniformity, your goal is to get a complete bigger disk which is uniform. So its sigma must be same. We cannot afford a variation in the value of sigma, that will make it non-uniform. For homogeneity, sigma must be same. And say its area is a dash and its mass is m dash. And you have to find this mass, how much mass is needed to fill that hole. So simply apply, since again it is uniform, m dash will be sigma into a dash. Sigma won't be dash, it is same for both the object being homogeneous. So put the value of sigma, that came to be 16 m divided by pi r square into 15. Now put a dash, the area of this smaller disk which need to be filled in that cavity. So it will be pi r by 4 square. So it will be pi r square by 16. So I'll get pi r square by 16. Now see, r square will be cancelled away, pi will be cancelled away, and 16 will be cancelled away. So I'll get m dash as m by 15. So this will be the required mass. This is the required mass of the disk which need to be filled in the hole to get a uniformity throughout. Okay. One approach is this. If you want to apply a shortcut approach, you can also do like this. Alternatively, but since in this first part was demanding the value of sigma, so we were going for the value of sigma by this lengthy approach, because by this approach shortcut we won't get the value of sigma. Simply you can apply, since the body are homogeneous, the ratio of masses will be equal to the ratio of areas. So this is your mass m1, that is m, and you can write area 1, and this is the smaller, its radius is r, and its radius is r by 4, and say the mass is m2 and area is a2. So you can simply write m1 by m2 is a1 by a2 and put the values of a1, a2, put m1 as m, m2 will come in terms of m. So but in this case, you are only finding the mass of this smaller disk which need to be filled in the hole. You are not finding the value of sigma. We did the problem by this approach by finding sigma because part A wants the value of sigma. Okay. So in such problem, first of all, take care whose mass is given, because that value will determine sigma, because the object whose mass will be given will have its area in the denominator, the same object. Now we are coming to a very important calculus skill. Right now, till now, you have seen the cases of uniform objects where the surface mass density is constant. Now we are going for a skill of calculus which will be applicable in many of the topics of 2-year course. A plane can be treated as a continuous assembly of a large number of elements of circular strips of infinitesimal. First key point. If you have any plane mean a flat surface. First key point. If you have any plane, like this board is a plane. If you see in your room, the wall in front of you is a plane, the floor is the plane, the ceiling is the plane. So a plane can be treated as a continuous assembly of a large number of elements of circular strips of infinitesimal width. Now let's see what it means. Suppose this is a plane and I'm making a circular strip like this, and I'm making again another circular strip. So I'm making a gap between them. So this are the calculus elements in form of circular strip. Okay, and see, say this is the all will have same center. They all are concentric. They all are concentric, all having the same center. And say this particular strip has a radius r, small r, and thickness. This is the white thickness. Can you see white pen thickness? So this is an infinitesimal thickness, very, very, very small thickness. Infinitesimal thickness. And something is infinitesimal, so it won't have a delta symbol, it will have dr. If you're taking the radius r, it will be dr. If you're taking the radius x, it will be dx. If you're taking the radius y, it will be dy. So I'm focusing just on one such element at a time, one such circular element at a time, whose radius is r and thickness is dr. Okay. Now this whole plane can be treated as an assembly of a large number of such circular elements, and they are continuous in nature with no gap, like this. Okay, say one is yellow, one is white. I'm making very thick thickness for the visibility. Actually, they will have a very negligible thickness. Okay, they will have a very negligible thickness. So just for the sake of visualization, I'm making different colors strip. Okay, so for each strip, R will be different, and they are continuous in nature. Strips are continuous in nature. That is, physically, one strip cannot be separated or isolated from another strip. Physically, one strip cannot be separated or isolated from another strip. The thickness is so thin, so negligible. And for each circle, for each element, circular element, these are circular element or circular strip, the radius r is variable, correct? See, as you are going away from the center, so small r is variable. It is changing for each strip. Okay. Now let's see. And what will be the area of one element? So see, suppose we have, let's say, an illustration. Suppose we have a disk of radius r. Okay. We have a disk of radius r. Of course, capital R is a constant. It cannot be changed. This is capital R, which is constant. Now, it is a plane surface, correct? We know disk is a plane surface. So, if you're taking an element in the form of circular element, you're taking a calculus element in the form of circular strip. This is the element in the form of circular strip. So, you are using the skill of taking circular strip in a plane. And say this strip has a radius small r and thickness dr. And this is one such strip. And there will be a very large number of so many of these strips continuous in nature. So when the strip is changing, small r is changing, correct? When you are changing this, we are just making representation of one strip. So small r is a variable. Okay. Now when you will take first strip, remember when you will take the first strip, so first strip will be at the center. So first strip is at center and it will be in the form of point circle. We know what is a point circle, which has 0 radius. So this is like first strip. For this, the value of small r is 0. R is beginning from here. You have seen how to run the linear variable in lecture 1, how we run the linear variable. So you're running r from C. So C is the origin of r. So for first strip, which is at the center, of disk, small r will have a value of 0. For the last strip, when you take the last strip, the last strip will be at the circumference or periphery or boundary of the disk, like this. So your last strip, when you're taking like this. This is your last strip covering the boundary of the disk, because now the surface region over which you're taking the disks were over. So this is the last strip, circular element, for which small r will be capital R. So you can see, and in between, this is the extremities, first strip and the last strip. And in between, there will be a very large number of strips with different value of r. So the limits of small r will be r is equal to 0 to small r is equal to capital R. These will be the limits of small r when you are changing the strip. Okay. Now, this is how we take the strip. All strips will have the same center, common center. You have just to denote one drawing of the strip, not you have to make multiple strips of radius r, where r is a variable, small r is a variable, capital R is of course a constant that is not related with the circular strip, that is the radius of the disk over which strips are taken. And this thickness is dr. Okay. First strip will be at the center, with which will be a point circle. So for this strip, small r will be 0. Last strip will cover the boundary or the circumference or the periphery of the disk, And for this, small r will be capital R. Okay, so R will run between 0 and capital R. Now we will come, what is the area of the strip? The second skill here is, what is the area of a strip? Now see, when we say area of a strip, what it means? It means area of material of a strip. It doesn't mean the area bounded by the strip. Don't get confused as the area bounded by the strip. So this was the disk of radius r. Okay, and here you are taken a strip, concentric strip of radius small r and thickness dr. So sometimes, students think the area of the strip is pi small r square. They think the area of the strip is pi small r square. No, this is basically the area bounded by the strip. Yes or no? This is the area bounded by the strip. You're applying the area of a circle. We have to find the area of this yellow colored ink, yellow colored region, yellow colored occupied space. This is the area you have to find. And see how we find this area. You imagine that you're cutting the strip. You are cutting the strip and you are stretching it. So when you cut the strip and stretch it, it will be like a straight line, correct? Stretching the strip. Now what will be the length of this strip? So it is the same this strip which was in the circular form. Now you have cut and stretched it. So length will be circumference, that is 2 pi small r. This is the length of the strip. What is the width? So width is the thickness, which is infinitesimal dr. So what will be the area of the yellow region? Now you have got a straight band in the form of like a rectangle, right? So what will be the area of this strip? That is the yellow colored region. So let's say length into breadth 2 pi r multiplied by dr. And when a finite quantity is multiplied by infinitesimal, the answer will be infinitesimal. So therefore, we write the area of a strip as dA as 2 pi r dr. Now remember this thing. This will be applicable frequently in almost now all the chapters of 2-year course. Whenever you are taking this is the first calculus skill in a plane. When we take a strip in a circular strip in a plane, so there are some basic fundamental points. First one is the strips are continuous in nature. You cannot separate, you cannot isolate one strip from another strip. Next point is the radius of the strip is small r and the thickness is dr. Third point is all the strips are concentric. Next point is for each strip, small r will be changing. As you are going away from the center, small r will be increasing. Like in this case, the strips are taken over a disk of radius capital R. So when you take the first strip at the center, it will be like a point circle with a small r is equal to 0. It will have no radius. When you take the last strip, which will be covering the disk, small r will be capital R. So r has a limits from 0 to capital R. Then we came, what is the area of the strip? So area of the strip doesn't mean area bounded by the strip. So don't get confused by thinking that this will be the answer. No, this is the area bounded. Area means this area, the area of the yellow color. So finding the area of the strip, you can imagine cutting the strip and stretching it, and you will get the length as 2 pi r and the breadth dr. So the area will be 2 pi r dr, and applying the basic concept of calculus, multiplication of a finite quantity with infinitesimal will be infinitesimal. So area will be written dA as 2 pi r dr. Okay. So these are the fingertip points. Now you will remember a plane can be treated as a continuous assembly of a large number of elements of circular strips of infinitesimal width. For each element, the radius r is variable. For a point circle element, r will be 0. The area of each element is 2 pi small r dr, and the mass of the element can be written as, and now suppose you have to write the mass of any circular you have to write the mass of any circular element which has a radius r and thickness dr in a plane. So mass you are writing as dm. So dm can be written as what? So we know the definition of sigma. Dm can be written as sigma into dA. And in electricity, you will write dq as sigma dA. In place of dm, there will be dq. Everything rest will remain the same. And dA will be what? Remember, don't derive every time while applying. Now you have to remember this as a fingertip point. For a circular strip in a plane, dA is 2 pi r dr. 2 pi r dr. This is for a circular element in a plane. Okay, so these are the basic fundamentals, and now we will see the application. It will get more clear in the problems to come, in the illustrations to come. You will get more clarity of these things. Now, first of all, let's see by this formula how we can derive the formula for the area of a circle. Now, we know from the childhood, if there is a circular plate of radius r, and if I say what is the area of this plate, so you'll say it's pi r square. Simple, that we are studying from right from childhood, correct? Remember this formula. Now we'll see how you can derive it with calculus. Let's see its derivation, the beauty of calculus, how the calculus will give you this formula. So suppose we have a circular region. Okay? Say of radius capital R. Okay, and we have to find what is the total area of the region. And we don't know this formula. We don't know pi r square. Okay, we have to derive this formula by calculus. So what we will do, we will apply the calculus. We'll take one element, circular element, in the form of a strip, concentric strip, say of radius, what, small r, and thickness dr. Correct? Now, the area of this strip will be how much? So right now we have seen it will be 2 pi small r dr. Okay, this is the area of this pink colored region, correct? This is the area of this pink colored circular strip. That is exactly the area of pink colored region. Now we have to find the total area of this circular region. That is the complete white area. So there will be a large number of such strips in this white surface, correct? That is the distribution of strips in a plane. There will be a very large number of such strips in this circular region, and for each strip small r will be changing. So if you have to find the complete white area, you have to find the area of white region. That is the area of complete circle. So you have to add this pink area for each of the strip. Add area of each strip, correct? So the complete area will, addition in calculus means integral of dA. So it will be integral of 2 pi r dr, and now you have to put the limit of r. R cannot be taken out of the integral, mind it. 2 pi will come out of integral, but r will not come out. For each strip, r is changing. So it will be something like this. Now integral is possible. R is the integrand, and the variable of integration is again r. With d it is r, so it is homogeneous. So put the limit of r. So for the first strip, r will be 0. Already we have seen. For the last strip, r will be capital R. So we'll get 2 pi r square by 2. Now put the limits 0 to capital R. So your area will come to be 2 pi r square by 2 minus 0 square by 2. Putting the limits, 2 will get cancelled away, and area will come to be pi r squared. This is the formula which you have been cramming or remembering right from childhood. So this can be derived by calculus. And which for this, you are not starting with the formula of the circle, mind it. You are starting with the formula of the rectangle. This formula has derived by the concept of the formula of the rectangular strip, correct? Like this, 2 pi r dr. 2 pi r dr was derived by the concept of the area of a rectangular strip, length into breadth. And when you are integrating this area, you are getting the area of the circle. So this is one of the beautiful, you can say, outcome of the calculus for deriving the formula of the circle. Now see, the next illustration, suppose we have uniform. Uniform means homogeneous. So we have a homogeneous or uniform disk of radius r and mass m. And the first part is find the surface mass density. So this is very straightforward. Yes or no? Very easy. Sigma will be total mass by total area, and we can apply this formula. Why? Because it is uniform or homogeneous. So I'll get m divided by pi r square. That is sigma. Already we did such kind of problem a little bit back. Now it is being said, consider an element in the form of a circular strip. Now you have to consider an element in the form of circular strip of radius small r and thickness dr, and write its mass. Now you have to write the mass of the strip. Say it's dm. Dm is the mass of a strip. So you remember dm will be what? Sigma into area of the strip. Right now we have seen basic. And I've told you, you have to remember this area of the circular strip. It's 2 pi r dr. So your dm will be 2 pi r dr, or you can write sigma 2 in front if you want. Sigma 2 pi r, order doesn't matter, dr. So this is the dm. That is the mass of this circular element. And you can put sigma as m by a. So you can also write dm as m by a, because you got the value of sigma 2 pi r dr. Got it? Now let's move ahead. Now see, now we are coming to another very beautiful application. Till now you were dealing with homogeneous surfaces. Surfaces where the mass was uniformly distributed. Now you have learned how to take a circular element. Now the question arises, when we have to take this circular element. One thing is there, I've seen most of the students write down the things when the teacher teach them. They simply copy it down. But when the new application comes in front of them, they find it hard to think, number one, whether calculus will be applied or not. And number two, if calculus is applied, then how it will be applied. Because in the class, teacher is telling you some particular problem, then you need not to employ this thinking. You will simply copy it down. But you will face a new problem, then you have to think two things. Whether the problem will involve calculus, number one, and number two, if calculus is involved, what will be the type of element, what will be the limits, what to be integrated or differentiated, all these things. So there are some criteria, some baseline which will tell you whether you will use calculus or not. If something is changing continuously, the basis of calculus is if something is changing continuously. See, the change can be in intervals or the change can be continuous. Suppose I'm driving the car from my office to my home and I'm changing my speed in every 10 minutes, finite intervals. For the first 10 minutes, I'm driving at 10 meter per second. For the next 10 minutes, I'm driving at 5 meter per second. So I'm changing the speed every 10 minutes in finite intervals. So here speed is changing, but the speed is not changing continuously. So you can also do the problem without calculus. But actually what happens when you drive the car? The speed fluctuates. The speed changes continuously. So if something is changing continuously from one point to another point, then it is the domain of the calculus. There you have to use the calculus. Okay. So suppose we have a uniform disk of radius r. No, it's written wrong. It can't be uniform. There is some typographical error because you cut down this uniform thing. It's not uniform. It's simply a disk of radius r where the surface mass density is. So you're given the surface mass density as a function of small r. Okay, and small r is the radial distance. That means the distance from the center. So the disk has a radius r, and Small r is denoting the distance from the center. So small r will depend at your location where you are standing. So this will be your small r, which is variable. Correct? For each point, small r will be changing. Yes or no? When you are going away from the center or you are coming towards the center, small r will be changing. So small r is variable. And since your value of sigma, bracket r means sigma as a function of r, it depends on small r. So sigma will also be changing with r because sigma depends on r. So it means sigma is also variable. And if sigma is variable, we don't have a uniform object because in uniform object, sigma is constant. So we have a non-uniform or non-homogeneous object. And whenever we have a non-uniform or non-homogeneous object, you cannot apply this equation. This equation has no applicability. You can just apply calculus. dm is equal to sigma dA. Whenever we have a non-uniform or non-homogeneous object, this can't be applied and we have to apply calculus because sigma is variable. So in the case of a variable sigma, when the object is non-homogeneous or non-uniform, one thing is for sure, we have to use calculus because something is changing from one point to another point. R is changing continuously. R is like the property of a point, correct? R is the distance of the point from the center. So for each point on the radial line, if you are going radially out, for each point R will be different. And if for each point R will be different, so for each point sigma will be different. So that's why we said sigma is a variable, which is making it a non-homogeneous object. So we have to apply calculus because some quantity is changing from one point to another point, number one. So one thing is for sure, how you decided that you have to apply calculus because the quantity sigma is continuously changing. Not only changing, it is continuously changing. Had it been changing in intervals, some finite radius segments, then we can do without calculus mathematics, which you'll see in the test and DPP. Okay, but here sigma is changing continuously. In the DPP, we cover both type of problem. Sigma is changing in continuous manner and in segmented, finite segmented manner. So in finite segmented manner, there is no use of calculus. You can also go it with simple maths. But when it is changing continuously, then we have to use calculus. Here, sigma is changing continuously. Now, one thing is decided, we have to use calculus. This change has suggested us that we have to use calculus. Now, the second point is, which kind of element? Now, the second question arises, because when you're using calculus, you will take some element. An element will depend on the nature of variation. So here, something is changing with R. It means at same R, the quantity will remain same. At same r from the center, sigma will remain same. It is only changing when you are moving away or towards the center. So in such cases, when something is changing with the radial distance in a plane, when something is changing, when something means some quantity depends on r in a plane, then you can take the element as a circular element. Okay, circular element. And already we have seen all the skills how we take the circular element. Okay, so we will take a circular element. So I'm taking this as a circular element of radius r and thickness dr. So this I'm taking as a circular element. Okay, now what will be the area of this element? Already you have seen all these skills I've taught you. So area I can directly write 2 pi, radius is r, thickness is dr. Okay, what will be the mass of this element? The mass we have to write dm, not m, but m, mass of the element. It's sigma into dA. So it is sigma into 2 pi r dr. This is the mass of this element, correct? Now suppose you have to find the mass of the disk. You have to find the mass of the disk. So the same thing, the disk will contain a large number of such elements distributed continuously. So you, for finding the mass of the disk, you have to add all the masses. So you can write m, say total masses, and addition in calculus means integral. Whenever you are adding infinitesimal, it means integral. So it will be integral of sigma 2 pi r dr. Now the question arises, what do you think? Will sigma come out of the integral? Will sigma come out? What do you think? The answer is no. Because sigma in this problem is variable. This is very important point. Sigma, like in lambda, linear mass density, when lambda was variable, it cannot be taken out of the integral. So here also sigma cannot be taken out because sigma is variable. Now the second challenge is 2 pi can be taken out. Now what is left is sigma r dr. Correct? Sigma r dr. Now there is a heterogeneity in the integral. The element of integration is r. How we decide the element of integration, we all know, no? The element with d. So it is r. Here it is r. But sigma is variable and is not known to which variable it depends. So for doing this integration, there must be homogeneity. That is a basic rule of integration we have seen in the basic lectures of integral. So sigma must be a function of r. Then only you can integrate. And that is given in the problem. That is given in the problem. Sigma is 2r. So given sigma is equal to 2r. I'm not writing sigma bracket r. That simply means sigma as a function of r. So I can write m as what? 2 pi. Put the value of sigma 2r dr. 1r is more there. 2r is the value of sigma. 1r was more there. Dr. Now bring this 2 outside. You'll get 4 pi r square dr. Now put the value of r. So we have a complete disk. There is no hollow cavity anywhere. So first strip will have r is equal to 0. That is the point strip at the center. And the last strip will have r is equal to capital R. That is the radius of the disk. So I'll get 4 pi, and this will be r cubed by 3 within the limits 0 to capital R. So I'll get 4 pi by 3 r cube minus 0 cube. So your answer will come to be 4 pi by 3 r cube. This is your answer. This is the mass of the disk. So this is how we proceed with such problem when sigma is variable. Okay. When you're finding the mass, first find the mass of particular strip dm, sigma dA, and then integrate, and don't bring sigma outside. Put sigma as a function of r, whatever is given. Got it? That is the first illustration for variable surface mass density. Now see the second illustration, same typographical mistake is there. It's written uniform. So please correct it. It's not uniform. Had it been uniform, then sigma would have been constant, and it's a problem of variable sigma. So now I think this you can do yourself. Simply there is another function. So I am leaving this as an exercise for you. The same approach will be there. And in DPP, there will be more problems for more practice and fluency. So you'll make a strip, correct, of radius r, thickness dr, and this disk has a radius capital R. So you can again, now you can work out dm is equal to what? Sigma dA, and dA will be sigma 2 pi r dr, and you will integrate as in the previous problem. So I'm leaving this as an exercise for you. And in DPP, you will also face some problem like this. Suppose the disk has some cavity, concentric cavity. Concentric means the cavity hollowness has the same center as the disk has. And this inner radius is A and the outer radius is B. This is also called annulus. Okay. So now see, here if you're taking an element, and say the radius of the element is small r and thickness is dr. So again the same thing, dA will be 2 pi r dr, dm will be sigma times of dA. But when you integrate, so the limits of r will change, because now we won't start the first circular element from the center. There is no mass at the center. This is a hollow cavity. So we won't integrate from the center. because no element can be taken in the center. The center is empty of mass. So the first element will be the inner wall of the cavity. The first circular element will be at the inner wall of the cavity. So R will begin with the limit of A, and the last element will be the periphery of the disk. So R will end at the value of B. Okay. So in such cases, you simply need to change the limits. Okay. Now see, if you have a semicircular disk that is half of a circle, say of radius capital R, and here you have to take a circular element. So in the same way, you'll take an element in the form of a semicircular strip, say of radius small r and thickness dr. Okay, so the area of a strip will be, so there was the area 2 pi r dr. 2 pi r dr was the area of complete strip, and this is half of the complete strip. So area will be dA is equal to divided by 2. It will be pi r dr. Correct. So in the case, if you have a semicircular plate, you'll take a semicircular strip with an area pi r dr. Okay. So this is the first lecture of surface mass density, where you have learned what is the value of sigma, what is the significance of sigma, how sigma is defined for homogeneous object, how the masses are divided in the ratio of the areas in case of homogeneous object. Correct. And then we have seen fingertip points. The ratios of masses will be same as the ratios of areas for MCQ as far as the object is homogeneous. Then we have seen some detailed working for homogeneous object. Then we have seen very important skill of calculus, which will be used throughout your 2-year course, taking a circular strip in a plane. Very important skill of calculus. There are many more skills like this, which will come in the subsequent lectures. 3 or 4 skills will be covered in the surface mass density. Then 3-4 skills will be covered in the volume mass density. Okay. So here in this lecture, you've seen how to take a circular element in a plane. It will be have a variable radius r, and the area will be 2 pi r dr. Its mass will be sigma dA. And for adding the complete mass, you can integrate. Okay. So this is your first lecture of surface mass density. And in the next lecture, we will see more skills like this skill we have seen in this lecture. Next lecture, we will cover the circular strip on a spherical surface like this, and then we'll see circular strip on a conical surface. And these are the very fundamental and important skill of calculus when you are finding different kind of quantities like gravitational field, moment of inertia, electric field, magnetic moment, so many quantities. So all such skills of calculus will remain the same. Okay. So what I suggest, first of all, you complete the related DPP of this lecture, and number 2, after doing the lecture, this one and CCD 1 and 02, I think you must have done before watching this lecture. So in the description given below, there is a test link. When you will click it, you will be redirected. It's a free test, so you can assess yourself for the innovative and new problems which appear in most standard competitive examinations. How you will encounter the new problems based on this concept. They will invoke your problem solving skills and call for the application of the concepts and fundamentals. So I'll meet in the next lecture with some more skill of calculus, like taking the circular element over a spherical surface.